Okay, so in this chapter we're talking about chi-square tests and contingency tables. One thing I want to say is that all the statistical tests we've examined so far have been designed to test hypotheses about specific population parameters. Because these tests all concern parameters and require assumptions about parameters, they're what's called parametric tests. Another general characteristic of parametric tests is that they require a numerical score for each individual in the sample. Often researchers are confronted with experimental situations that do not conform to the requirements of parametric tests. In these situations, it may not be appropriate to use a parametric test. So for example, when the assumptions of a test are violated, the test may lead to an erroneous interpretation. There are several hypothesis testing techniques that provide alternatives to parametric tests. These alternatives are called nonparametric tests. Now, our book separates chi-square and contingency tables into chapter 11 and nonparametric statistics into chapter 13, but they're all nonparametric statistics, so I wanted to introduce this now. Okay, so occasionally you have a choice between using a parametric and a nonparametric test. In most situations, the parametric test is preferred because it's more likely to detect a real significance or a real difference or real relationship. However, there are situations for which transforming scores into categories might be a better choice. It may be simpler to obtain category measurements, for example, high, medium, and low income, than to actually get everybody's actual income. So the original scores may also violate some of the basic assumptions that underlie certain statistical procedures. So if that happens, you can use nonparametric tests. So the chi-square test for goodness of fit, you might see me write this as GOF, uses sample data to test hypotheses about the shape or proportion of a population. The test determines how well the obtained sample proportions fit the population proportions specified by the null. So this is similar to a test that we've already learned. When we did the one sample t-test, we used a sample to test a hypothesis about one parameter. So this is also known as the one sample case, but it indicates whether or not the observed frequencies are a good fit to the expected frequencies. There's one variable that contains two or more categories, and the observed frequencies are obtained through data collection and expected frequencies are given. Data is measured at the categorical, which is also called nominal or ordinal level. So the null hypothesis is that there's no difference in proportions. We use this in situations in which a researcher wants to determine whether the proportions differ from one category to another. We also could say there's no difference from a known population. So we use this when a specific population distribution is already known. For example, if it's known that 28% of licensed drivers are younger than 30 years old, so 72% are older than 30. And then the observed frequencies, the actual number of individuals from the sample who are classified in a particular category. Each individual is counted in one and only one category. The expected frequency is the value that is predicted from the proportions in the null hypothesis and the sample size. The expected frequencies define an ideal, hypothetical sample distribution that would be obtained if the sample proportions were in perfect agreement with the proportions specified in the null. Okay, so how do we find the chi-square? So in Greek, the x is a chi, and when we square it, we get the chi-square. If I were to take the square root of this value, I would get a z-score. The sigma means sum, so we have our observed frequency minus the expected frequency. We take that value and we square it, and we divide by the expected frequency. And then we sum all of those and compare it to the test statistic, but the computer will do this for us. So I wanted to just show you how to find the expected frequency. So here we have a little 2x2 table. We have males and females and Democrats and Republicans. All right, I'm going to show you how to do it for this cell, okay? So to do the expected frequency, we take the row total times the column total divided by the grand total. So for this cell, we know the observed frequency of male Democrats is 25, but we would expect that we would get 42 here. So how do I get that? I take my row total, 85, times my column total, which is 100, divided by the grand total, which is 200. So I get 8,500 over 200 and 42.5. When I do these by hand, I put a little slash here, and I write the expected value for each of these values. And then that way I do the observed minus the expected, square it, write it down, divided by the expected. All right. And then your degrees of freedom are row minus 1 times column minus 1. Well, since we only have 2 rows and 2 columns, 2 minus 1 times 2 minus 1 is 1 times 1, which is equal to 1. So for a 2 by 2 contingency table, our degrees of freedom is 1. All right. Note, the formula for chi-square involves adding squared values, so you can never have a negative, and all chi-square values are 0 or larger. When the null is true, we expect the chi-square values to be small. And the bigger the difference between the observed and the expected, the larger the chi-square value and the more chance that it will be significant. Now, this is a skewed distribution. If you remember back in the day, we talked about this is a right skew. And so our critical region is down in this area. And our degrees of freedom is determined by the category minus 1 for a one sample chi-square, or a goodness of fit test, where C is the number of categories you're comparing. And so like I say, how would you describe this? A right skew. All right, in probability theory and statistics, the chi-square distribution, also called chi-squared or chi, written out with the Greek letter distribution, with k degrees of freedom, which means any degrees of freedom, is the distribution of a sum of squares of k independent standard normal random variables. The chi-square distribution is a special case of the gamma distribution and is one of the most widely used probability distributions in inferential statistics. And I wanted to show you this because when we have a degree of freedom of 1, we have this highly skewed distribution. But as we increase our sample size, what happens? The central limit theorem goes into effect, and we get what looks more and more normal. All right, so I'm going to read this example from page 506. Okay. A random sample of 100 weights of Californians is obtained, and the last digits of those weights are summarized in table 11.2. When obtaining weights of subjects, it is extremely important to accurately measure their weights instead of asking them to report their weights. By analyzing the last digit of weights, researchers can verify that they were obtained through actual measurements instead of being reported. When people report their weights, they tend to round down and often round way down. So a weight of 197 pounds may be rounded down as the more desirable 170 pounds. Reported weights tend to have many last digits that consist of 0 or 5. In contrast, if people are actually weighed, the weights tend to have last digits that are uniformly distributed with 0, 1, 2, all the way to 9, all occurring with roughly the same frequencies. We could subjectively examine the frequencies in table 11.2 to see that the digits of 0s and 5s do seem to occur much more often than the other digits. But we're going to proceed with the formal hypothesis test to reinforce that subjective conclusion. All right, so we're going to test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. So let's look at our data. We have a null hypothesis that all probabilities are equal, and the alternate that at least one of the probabilities is not equal. So the last digit of 0 is 46. There, the last digit of 1, somebody reported it as 1. 2 and 2, 3 and 3, 4 and 3, 5 and 30. So this is kind of supporting our hypothesis, or the claim that when people report their own weights, they tend to round to 0 or 5. So we're going to test this and see if we get a significant finding. So we enter the data, and here we're going to, each of these is a category. So each one, this is being treated as a category. So how many people chose 0? 46. How many people chose 1? 1. How many people chose 2, etc. So we enter our data into 2 columns, and then we're going to go into data, go all the way down to frequency and weight cases by frequency, hit OK. And then we're going to go to Analyze, Non-Parametric Tests, One Sample. All right, this comes up. And then the first thing we're going to do is we're going to choose the Fields tab. And we're going to say, let's customize our analysis. All right, we could automatically compare observed data to hypothesized, but sometimes the computer will do something screwy, so we want to do it this way because you're going to have to do this in the next example. So I'm going to show it to you here. So we customize on analysis, and we click fields, and sometimes it will do it for us. It'll put the nominal over here, but we want to make sure that our continuous variable is here, and our test field is the nominal variable. All right, and then we're going to click Settings, all right, before we hit Run. And when we hit Settings, we get this dialog box. And we're going to customize tests, and we're going to compare observed probabilities to hypothesized, and we're going to click Options. And the reason why I'm showing you this is because we have to do it the next time. Here, it's auto-populated to all categories have equal probability. The next time we're going to do this one, but right now we're just going to leave it here. We're going to click OK, and then we're going to go back and click Run. All right, now the output's really nice. It tells us what to do. It tells us, hey, reject the null hypothesis. Here's our n, here's our chi-square value, here's our degrees of freedom, and here's our p-value. So we say chi-square of 8, which we write the degrees of freedom first, comma, sample size is equal to the chi-square value, p is less than 0.01. Now, I think in your version of SPSS, you don't get the tables unless you double-click this output. So there's somewhere where you click, it says double-click to activate. You double-click it, and it'll pop up these tables. All right, so really quick, the phi is the measure and effect size for a 2x2 table. And I'm less concerned about the phi, but I just wanted you to see it because you're going to see phi in Kramer's V. You can go here and use the calculator and find your phi. And phi is just the Greek letter F. It's this weird little squiggle. That's the Greek letter F, and it's just a 2x2 contingency table. The phi and the Kramer's V are equal. So just bear this in mind. If we did this out, we calculate it with this calculator, we get a phi of 1.81, which is a large effect size. Okay, and then it gives us these tables, and you can see that the expected value, the observed value, is very different than the expected for the 0 and for the 5, which is what we could see just by looking at the data. Okay, let's do a different one. All right, here's another one from the textbook on page 508, example 2. According to Binford's law, a variety of different data sets include numbers with leading first digits that follow the distribution shown in the first two rows of table 11.4. Data sets that tend to follow Binford's law include a class of errors in clinical trials as well as magnitudes of gradients from MRIs, CTs, and ultrasound images. The bottom row of table 11.4 lists the frequencies of leading digits of the magnitude of gradients from the ultrasound image. Do the frequencies of leading digits in the bottom row appear to fit the distribution of Binford's law as expected, which would be the middle row, or does it appear to be that the image has been corrupted with a substantial amount of noise because the leading digits do not fit the distribution? So let me explain that. So what we have here is, it's just like in this one, and the other one rather, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of them occurring at 10% each for each category, according to this Binford's law, they should occur at this frequency or at this expected value. And here we see we have the actual observed value. So we need to input this into the computer. All right, so we do the same thing. We have the leading digit. We're going to do 1 through 9. We have the frequency. Now this, I put the probability value, so we have 30.1, so I write it in as 0.301. And we really don't do anything with this last column, but instead of having it on a scrap of paper somewhere, I put it into my data set so that it's there for, all time. And when I'm loading the information, having it here in the data view is very helpful. So what we're going to do is we're going to manually enter the probability. So remember, we have to weight the cases by frequency. And I'm going to show you how to manually enter them. You go to Analyze, Nonparametric, One Sample. And I say don't do this from the output screen. You want to do it from the data view screen, and I'll show you why. So we go to Analyze, Nonparametric, One Sample. And then here I'm in the data view, right? And so now I do all the same things that I did before. Let me scroll back. All right, I get to this point, I get to settings. I go to fields, I make sure I have the categorical variable in the test field. Then I click settings. I say compare to hypothesized chi-square. I hit options, and instead of going here, I do customize. So here I click customize, which I believe I show you here. Customize the expected probability, and now I'm going to type in for category 1, I expect this probability value. So category 1, 0.301. Category 2, 0.176. I just highlight the first two to show you what I'm doing, but you do all of them. Then you click OK, and then you go back and you click Run. Okay, so again, it tells us what decision to make, which is retain the null hypothesis. And it gives us some pretty figures if we double click to activate. We fail to reject the null and conclude that there is not enough evidence to warrant rejection of the claim that the 271 leading digits fit the distribution given by Benford's law, and there isn't enough evidence that the ultrasound readings have been corrupted with noise. So we say chi-square of 8, n is equal to 271 is equal to 11.3, p of 0.19. All right. So now we're looking at the chi-square test of independence. The chi-square test of independence determines whether there's an association between categorical variables, whether the variables are independent or related, and it is also a nonparametric test. It's also referred to as the chi-square test of association. This test utilizes a contingency table to analyze the data. A contingency table, also known as a cross-tabulation, cross-tab, or two-way table, is an arrangement in which the data is classified according to two categorical variables. The categories for one variable appear in the rows, and the categories for the other variable appear in the columns. Each variable must have two or more categories. Each cell reflects the total count of cases for a specific pair of categories. Okay. It's commonly used to test the statistical independence or association between two or more categorical variables. It cannot make comparisons between continuous variables or between categorical and continuous variables. Additionally, the chi-square test of independence only assesses associations and can't provide any inferences about causation. If your categorical variables represent a pre-test and a post-test observation, then the chi-square test of independence is not appropriate. This is because the assumption of the independence of observations is violated. In this situation, McNemar's test is appropriate for dichotomous variables. Chapter 13 will cover a different technique. So what are our data requirements? Two categorical variables. So what are our data requirements? Two categorical variables, two or more categories or groups for each variable, independence of observations. There is no relationship between the subjects in each group. The categorical variables are not paired in any way, like a pretest or a post-test. And that we have a relatively large sample size. Expected frequencies for each cell are at least 1, and there should be at least 5 in each of the cells. So our hypothesis for these are that the null hypothesis is that variable 1 is not associated with variable 2, and our alternate is that variable 1 is associated with variable 2. So how is this like what we've already learned? Because it evaluates the independence between populations represented by two independent samples, it's somewhat like an independent samples t-test. And because it tests the association between variables, it's also like a correlation. And then this is just kind of a reiteration of how I showed you how to calculate the expected frequency, and it's just this different way of writing. We have the row sum and the column sum, and we have our expected value, our observed minus expected squared over the expected. And then also if our significant value is less than 0.05, we're going to reject the null hypothesis. So there's two different ways in which our data can be set up. The format of the data will determine how to proceed with running the chi-square test of independence. At minimum, your data should have at least two categorical variables represented in columns that will be used in the analysis. The categorical variables must include at least two groups. Your data may be formatted in either of the following ways. So this way, you have one row. This is a person, and this is that person's value on this categorical variable. So either they're a smoker, a non-smoker, or a current smoker, past smoker, or a non-smoker. So this person's a non-smoker and he's male. This person's a past smoker and she's female. Cases represent subjects and each subject appears once in the data set. The data set contains at least two nominal categorical variables. It could be string or numeric. And they must have at least two or more categories. Okay, so this is fine, but if you have a contingency table that's presented to you, you don't want to have to go in and type this 435 times. So if you get it this way as a 2x2 table or a 2x3 table, you can do it this way. And like I've showed you before, this is a freshman who picked a major, and of those, there are 212 of those people, freshmen who did not pick a major. And this is a freshman who did pick a major, and there's 114 of those. Sophomore who didn't, sophomore who did, and the counts. And then we would weight by the frequency. All right, so the research question is there an association between gender and smoking? The null is that there's no association, and the alternate is that there is. So we get to analyze descriptives, crosstabs. We bring smoking to the rows and columns, gender to the columns. All right, then we're going to click statistics and we're going to bring up chi-square and we're going to check our phi and Kramer's V. Okay, and then we're going to click continue and take us to the next page. Then we're going to click cells and we're going to do expected and row. And then we're going to say, okay, oh, and one thing I forgot. Over here, we want to click display clustered bar charts. Okay, so when we evaluate the output, we can see this is pretty close, this is pretty close, and this is pretty close. And so we probably won't see an association. And in fact, we don't see association because here we have a p-value of 0.21, and we'll need this information to write up our findings, and we see that our phi and Kramer's V are pretty small. Okay, so if we wanted to do a post hoc test, we would look at the expected count and the actual count. And since we didn't have significance, we're going to see these guys to be pretty similar, 149, 142, 148, 154. But say we come down here and we see that our expected count is 35 and we find that we have 95 here, for example. Current smoker, who's also a female, that would be where we would find the difference. It's kind of like doing a post hoc. And it can get a little bit more complicated actually finding the p-values and such, but this just gives you kind of a ballpark idea about where those differences lie. So we're going to state our conclusion. The results indicate that there is no significant association between smoking and gender, and then we write it out. Okay, and then here's the Kramer's V, just the calculation. I'm showing it to you. For each degree of freedom, the benchmarks are a little bit different. You can go to this website, which I've showed you before. The nice thing about this is if you get presented with a contingency table and you want to check that you inputted it into SPSS correctly, you can throw it into this and see what your values are and check yourself. Okay, so let's do another one. So here's the research question. Is there an association between living on campus and class rank? We're just looking at this data set that we'd used before with the smoking. And we see rank, upperclassmen, upper or lower class, and live on campus. So our null is that there's no association between living on campus and class rank, and the alternate is that there is an association between living on campus and class rank. We do the same things that we want. We go bring rank and upper over and live on campus, chi-square, phi and Kramer's V, check the display clustered bar charts, and then we see that there's a little difference here and there's a big difference here. So now there appears to be an association between the upperclassmen and lowerclassmen groups and whether or not they live on or off campus. This shows differences between the groups over the two levels of on-off campus. And then we have our 2x2 tables. We see that we have significance. We have a 1 degree of freedom with 388 valid cases, and our phi and Kramer's phi. And this one's negative, and I've read online that it has to do with the phi being a directional hypothesis, so we're just going to stick with the Kramer's phi. And we state our conclusion that the results indicate that there is a significant association between rank and on-off campus, and then we write it out. Okay, so the chi-square test of homogeneity is just the same thing. It's just the way you phrase your research question. Instead of we're looking at the independence between row and columns, we're seeing if they have the same proportion of some characteristic. So for example, in a study of the eating habits of children, a nutritionist selects a random sample of 300 first graders, 150 boys and 150 girls. Each child is asked how many times they eat fast food, 1 time a week, 2 times a week, or more than 3 times a week. So the null would be that the proportions for each choice are the same between boys and girls, and the alternate would be that at least one is different. And so I'm not going to do all the calculations. I'm just going to show you. The results show that there is a significant, so we would conclude that the proportions for each choice are not the same for boys and girls. And that's how you do the test of homogeneity. All right, so this is strictly for a 2x2 table when one cell violates our kind of assumption that we need to have at least 5 expected frequencies. When we have little numbers like 4 or less than 5, we can do a Fisher's exact test. And I have this here, this Google lady tasting tea experiment. Ronald Fisher is the one who came up with this, and his secretary said that she could tell whether or not you poured the tea in the cup before the milk or the milk before the tea. And he didn't believe her, so he devised this test, and I'll let you go read that on Google to see how it turned out. So example 3 on page 520, test the question whether people exposed to yawning make someone yawn. With these data, we run a crosstab. So when I say, when you're presented with a contingency table and you have a 10, a 4, and a 24, and a 12, if you want to use that Vassar stats, you just plug it in just like this instead of having to do it this way. And that's a good way to check that you've done it correctly. So if you were exposed to yawning, did you yawn? Yes or no? If you were not exposed to yawning, did you yawn? Yes or no? And so these are the counts. And we want to just test the Fisher's exact test. We want to use that one because it's appropriate to use in this situation. Okay, so we labeled them 1, 2, 3, 4. So did yawn, I could have shown you the value labels here as well, but 1 and 1 is yes, yes. 2 and 1 is no, yes. 3 and 2 is yes, yes. And 4 and 2 is yes, no, no. I think I got that right. Okay, so we run the test and we go to Fisher's exact test and we come across and we see that there is no significance, so that there is no relationship between yawning and whether or not you saw somebody else yawn. All right, so like I said before, the McNemore's test for matched pairs is when we have matched pairs, right? One of the assumptions of the chi-square test of independence is that they're independent. And so when you have paired samples, like measurements from right ear, left ear, like I say here, or, repeated measures like pre-test, post-test, then you would want to use this McNemore's test. And the variables in both row and columns have to be dichotomous, so it's got to be a 2x2. So we go to analyze descriptors, crosstabs, same, everything's the same, like we know. Here we're looking at hip protector worn and whether or not they had a fracture, and no hip protector worn or hip protector worn, and whether or not they had a fraction. So we enter our data, we do all the same things, we go to chi-square, and here I check chi-square and McNemore, and then we get this output. I've got a bunch of stuff going on here, and I'll walk you through it. So the first thing is we can see that the results are not significant. Here they're not significant, here they're not significant, here they're not significant, all the way down. None of it is significant. So there's no significant relationship or difference if you wear a hip protector or not, and whether or not you get a fracture. So if I just check McNemore, this is my output. If I just check chi-square, this is my output. But if I check chi-square and McNemore, I get all of it. So I usually just check both. And that's how we figure that out. So last thing on nonparametric statistics. This chapter is kind of like a restaurant menu of different tests you can do when you have different perspectives on questions regarding independence or associations between categorical variables. Me, myself, I don't even remember how to do all of these in SPSS when I'm doing my own research. My intention here is to give you a reference to use when or if you need to do these tests. I use Google a lot when I have to do an obscure test. I don't remember exactly. I know what they are and that they exist. And when reviewers of your work might say, well, you violated this assumption, why didn't you do it non-parametric? I typically do both. I published a paper where I had parametric, just a t-test, and they balked at it and said, you have a small sample size, you should have done a non-parametric. So I did both and then reported both. I had significance in the parametric and in the non-parametric and called it a day, and it was accepted. So in the next chapter, we're going to cover another menu of non-parametric equivalents of parametric tests we've learned so far. But just know that there are many, many out there, and if you violate some assumption, don't feel like that's it, you're done. You can go and again ask Google, look around. There may be some non-parametric equivalent that you can do. All right.